So let me continue with simultaneous equations, solution of simultaneous equations. Let me take up one more example pertaining to solution of simultaneous equations. Investigate for what values of lambda and mu the system of equations x plus y plus z equals 6, x plus 2y plus 3z equal 10, and x plus 2y plus lambda z equal to mu. Investigate for what values of lambda and mu. There is a lambda over here and mu over here. For what value of lambda and mu, the system of equations has a unique solution, infinite solutions, or no solution. Okay, so let me first write down the matrix representation of this system. The matrix representation of this system is given by one, 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 6, 1, 2, 3, 10, 1, 2, 3, 10. Then 1, 2, lambda mu. 1, 2, lambda and mu. Now what is the procedure? We have to find rank. This is A, x equal to B. We have to find rank of A, then rank of A, B, and then we have to conclude whether it would have a unique solution, whether the system is consistent, first of all, then whether it has a unique solution, infinite solution, or no solutions. So for that, I have to make these two 0, which is very easy. So let me operate. See, I can make this 1, 2. Here again this is 1, 2. Let me operate like this, operating row 3 minus row 2. Row 3 minus row 2. What is that? 1, 1, 1. This is x. This is 6. I have not done anything with regard to row 1 and row 2. Now I am operating row 3 minus row 2. 1 minus 1 is 0. 2 minus 2 is 0. And lambda minus 3. And it will be mu minus 10. Fine. Now again I can make this one 0 or this one 0 with the help of this. This is a diagonal element, we cannot make this equal to 0. So let me operate row 2 minus row 1. Row 2 minus row 1. What I will get? 1, 1, 1. This is x. This is 6. Now row 2 minus row 1. 1 minus 1 is 0. 2 minus 1 is 1. 3 minus 1 is 2. And this is 10 minus 6, it is 4. Then row 3 is as it is 0, 0, lambda minus 3 and mu minus 10. Now we can now conclude whatever we want to, because we don't need anything now. We can calculate from this only. This is A, this is x, and this is B. See, what is the rank of this A? Your A is what? It is 1, 1, 1, 0, 1, 2, 1, 0, and lambda minus 3. See, rank of this matrix, this is 0. rank of this matrix will be 2 if lambda minus 3 is 0. Okay, if lambda minus 3 is not equal to 0, then rank will be 3. If there is a 0 quantity over here, means lambda minus 3 is 0, then rank is 2. If there is a non-singular, non-zero quantity over here, then rank is 3. So it depends on lambda minus 3. Whether lambda minus 3 is 0 or lambda minus 3 is not equal to 0. And your AB, matrix AB is what? 1, 0, 0, 1, 1, 0, 1, 2, lambda minus 3, and then 6, 4, mu minus 10. Now let me take case 1. If lambda minus 3 is not equal to 0, that is if lambda is not equal to 3, and mu minus 10, it doesn't really matter whether mu minus 10 is 0 or it is not equal to 0, because in both cases there will be a minor of order 3 which is not equal to 0, so rank will be 3. So mu minus 10 is equal to 0 or is not equal to 0, means whether mu is equal to 10 or mu is not equal to 10, then rank of A is rank of AB is equal to 3. See, if lambda minus 3 is not equal to 0, rank is 3. This will be part of this AB. There will be at least one minor of order 3 which is not equal to 0. So rank is 3 in both cases. So rank of A is rank of AB is 3 and unknowns are 3, equal to the number of unknowns. So the system is consistent and will possess unique solution. So this is our case 1. So whether lambda is not, if lambda is not equal to 3, whether mu is equal to 10 or mu is not equal to 0, doesn't matter. Rank of A and AB will be same and number of unknowns are also 3, same. So system will be consistent and will possess unique solution. Now, if lambda minus 3 is not equal to 0, if lambda minus 3 is equal to 0, that is if lambda is equal to 3, and this is second case, and mu minus 10 is also equal to 0, that is mu is equal to 10. See, if lambda minus 3 is equal to 0, rank is 2. So rank is 2, but if mu minus 10 is not equal to 0, then rank will be 3. Rank of AB will be 3 if mu minus 10 is not equal to 0. Therefore, in order to have a solution, in order to have this system to be consistent, mu minus 10 must be equal to 0. So if lambda, this is also 0, then rank is again 2 for AB. But if it is not the case, then we have a problem that will be discussed in next case. So if lambda minus 3 is 0, that is if lambda is 3 and mu minus 10 is 0, that is mu is 10, then rank of A is equal to rank of AB is equal to 2, which is less than 3, the number of unknowns. Okay? Again see, if lambda minus 3 is 0, so rank will be 2. If mu minus 10 is also 0, rank will be 2. So rank of A is rank of AB is 2, which is less than 3, the number of unknowns. So system is consistent and will possess infinite solutions. Infinite solutions. Fine? Now, case third. If lambda minus 3 is 0, that is if lambda is equal to 3 and mu minus 10 is not equal to 0, that is if MIB is not equal to 10, then rank of A is 2, but rank of AB is 3. Rank of this is 0, so rank of A is 2. But if this is not 0, then there will be at least 1 minus order 3, which is not equal to 0. Therefore, rank will be 3. So, rank of A is not equal to rank of AB. So, system is inconsistent and no solution. No solution. Fine. So, you can have as many solutions as many questions as you have. I have already forwarded notes to you. I have already forwarded exercises to you. There are so many things you can do of your own. So please do it. I will be taking next chapter, next sub unit. Or let me give you one more example. Let me investigate for what value of lambda the system of equations x plus y plus z equal to 1, x plus 2y plus 4z equal to lambda, and x plus 4y plus 10z equal to lambda square has a solution. Let me investigate for what value of lambda. There is 1, lambda and lambda square. For what value of lambda this system has a solution. I don't have to find the values which doesn't have solution. For what value of lambda I don't have a solution. I have to see for what value of lambda this system has a solution. And let me solve in each case and solve or find the solution in each case, because the lambda square, it will be a quadratic in lambda. You will have two values of lambda each case. Now see how to proceed. Same procedure is there. You have to first see the matrix form of this system. It is 1, 1, 1 and 1, 1, 2, 4 and lambda, 1, 4, 10 lambda square. So again, let me make this 0 with the help of this, or let me operate row 2 minus row 1, row 3 minus row 1. You will get 1, 1, 1. Row 2 minus row 1. 1 minus 1 is 0. 2 minus 1 is 1. 4 minus 1 is 3. And this is lambda minus 1. Then row 3 minus row 1. 1 minus 1 is 0. 4 minus 1 is 3. 10 minus 1 is 9. Then lambda square minus 1. Now you can make this 0 with the help of this. Operate row 3 minus thrice row 2. What we will get? 1, 1, 1, 0, 1, 3, 0, 3, 9, 0, 0, 0. Row 3 minus thrice. 3 1s are 3, 3 3s are 9. So 0, 0, 0 x equal 1 lambda minus 1, lambda square minus 1 minus 3 times lambda minus 1. Row 2, row 3 minus thrice row 1. Row 2, right? Sorry. So finally what we are getting is the following. 1, 1, 1, 0, 1, 3, 0, 0, 0, x, y, z equal 1 lambda minus 1. Then you have lambda square minus 1 minus 3 lambda plus 3. So it is lambda square minus 3 lambda plus 2. Now see, this is A. Now what is the rank of this? This is A, X, and this is B. See, rank of this matrix is 2. Clear, because one row is 0. Rank of A is 2. You have a unit matrix of order 2 which is not equal to 0. Or a minor of order 2 which is not equal to 0. At least one minor of order 2 which is not equal to 0. So rank is 2. But if you will combine these two, there will be this and this column. 1 lambda minus 1 lambda square minus 3 lambda plus 2. Let me write down AB. Your AB 1 0 0 1 1 0 1 3 0 1 lambda minus 1. See, this is a quadratic equation. Lambda square minus 3 lambda. What is lambda? It is minus b under root of 3 square. It is 9 minus 4 to 8 by 2. 3 plus minus 1 by 2. So this is lambda equal to lambda 3 plus 1 is 2. 3 minus 1 is 1. So these are two values. Okay, let me write lambda square 3 lambda plus 2. See, this is A. Obviously rank of A is 2, but AB, if this is non-zero, then rank of AB will be 3. So no solution. But I have to see for what value of lambda this system will have a solution. So this system will have a solution only when this quadratic equation is 0. Okay. So let me write down the above system will possess a solution only if lambda square minus 3 lambda plus 2 equals 0. That is, if lambda is equal to 1 and 2. If this is 0, then rank of A is 2 and rank of AB is 2, which is less than 3, the number of unknowns, and we will have a unique solution. So I will have a solution only when lambda is 1 and lambda is equal to 2. Otherwise, I don't have a solution. Now let me solve for lambda equal to 1 as well as lambda equal to 2. Now when lambda is equal to 1, what I will get from A means from this one, I will get 1 1 1 0 1 3 0 0 0 x y z is equal, lambda is 1 now, 1 0 and 0. This is root of the quadratic equation, so this will satisfy it. Okay. Now let me see what are the equations. From this I will have, let me call this B. From B I have 1x plus y plus z is equal to 1. 0x y plus 3z equals 0. First of all, let me tell you, rank of A is 2, rank of AB is 2. Less than 3, the number of unknowns. System is consistent and will possess infinite solution. You will get infinite solution from this. Say this, if this is A1, this is A2 or B1. From B1, you will get y is equal to minus 3z. That is, y is equal to minus 3k1, while z is equal to k1. Okay, let me suppose that z is k1, I will get y equal to minus k1. And from A1, I will have x equal to 1 minus y minus z. It is 1 minus y. What is y? Minus 3. So plus 3k1 minus k1. Your y is minus 3k1, so minus minus plus 3k1. So my x is 2k1 plus 1. Therefore, when lambda is equal to 1, for lambda equal to 1, my x, which is x, y, z, is equal to 2k1 plus 1. Your y is minus 3k1 and z is k1. So I had observed earlier that rank of A is 2, rank of AB is 2, which is less than 3, the number of unknowns, system is consistent and will possess infinite solutions. These are the infinite solutions. For different values of k1, I will have different values of this x. So you have infinite number of solutions. Similarly, for lambda equal to for lambda equal to 2, what I will get? I will have 1 1 1 from this A, 0 1 3 0 0 0 x y z. Now lambda is 2. 1 2 minus 1 is 1, and this is 0 because this is the root of the equation. So you can see rank of A is 2, rank of AB is 2, and unknowns are 3, infinite solutions which are given by this. Say this is C. From this you will get x plus y plus z equal to 1. Say this is A2. Y plus 3z equal to 1. This is B2. From B2, y is equal to 1 minus 3z. So y is equal to 1 minus 3k2. Your z is equal to k2. I have taken z as k2. And from A2, x is equal to 1 minus y minus z. It is 1 minus y, it is y, this is y. Minus 3k2 minus 1 minus z, it is k2. So your x is 1 and 1 goes, minus 4k2. Therefore, for lambda equal to 2, your x, which is x, y, z over here, is minus 4k2, 1 minus 3k2, and k2. So infinite solutions. For different values of k2, you will have infinite different values of this system. So this is it. This is all about simultaneous equations, solution of simultaneous equations. You can have more questions on it. I have already forwarded a lot of questions to you. Solve it. If there is any difficulty, you can consult me. Now let me come to eigenvalues and eigenvectors. Eigenvalues and eigenvectors. See, now let me define a few things. Characteristic matrix. Let A equal to Aij be a square matrix of order n. Now we are dealing with only square matrices over here. Eigenvalues and eigenvectors. In eigenvalues and eigenvectors, we are dealing with only square matrices. So let A equal to Aij be a square matrix of order n. Then A minus lambda I, where lambda is a scalar and I is a unit matrix of order n. Of order n. Means that if A is a matrix of order 3, square matrix of order 3, I will be a square matrix of order 3. If A is a unit matrix of order 4, I also will be a matrix of order 4. So if A is a square matrix of order n, I also will be a square matrix of order n. Then A minus lambda I, where lambda is a scalar, I is a unit matrix of order n, is called the characteristic matrix. Matrix of A. A minus lambda is known as the characteristic matrix of A. Means your if, that is if A is A A11, A12, A13. Okay, let me write square matrix of order n. A1n, A21, A22, A2n, AN1, AN2, ANN. This is a square matrix of order n. Then A minus lambda I is A11, A12, A1n, A21, A22, A2n, AN1, AN2, ANN minus lambda I. I is 1, 0, 0, 0, 1, 0, 0, 0, 1. A minus lambda I is the characteristic matrix. Or A11 minus lambda A12 A1n A21 A22 A2n AN1 AN2 ANN minus lambda. You see, this is lambda times. So lambda, when you will multiply lambda to a unit matrix, this will be in diagonal only. Lambda minus lambda. So if you will subtract two matrices, you will be having lambda in the diagonal minus lambda in the diagonal. So characteristic matrix of a unit matrix A is nothing but the matrix itself, but minus times the diagonal elements, minus times lambda times the diagonal elements. So A11 lambda, A22 lambda, ANN lambda, and so on. This is the characteristics matrix. The characteristic polynomial of A is given by determinant of A minus lambda I. If you will find, this is the characteristic matrix, if you find its determinant, this will be a polynomial of degree n. Let me tell you, if you have a square matrix of order n, determinant of A minus lambda I will be a polynomial of degree n. If it's a square matrix of order 2, you will get a quadratic of quadratic. If you have a polynomial of degree, quadratic matrix of order 3, you will get a polynomial of degree 3, and so on. Right? This is the characteristic polynomial. And the characteristic equation, which is very important for this, characteristic equation of A is given by determinant of A minus lambda I equal to 0. Means the characteristic polynomial, when equated to 0, becomes an equation known as the characteristic equation of A. So the characteristic equation of A is given by lambda n. You can have A n lambda n, A n minus 1 lambda n minus 1. This will be a polynomial equation. A0I equal to 0. This is a characteristic equation of A. Always be a polynomial equation, right? Characteristic equation, right? So let me take up an example. For example, and let me tell you, this is a polynomial n. It will have n roots. The roots of, this is important, characteristic equation are called the eigenvalues. Eigenvalues or latent values of A. Okay, now let me take up an example. 1, 4, 3, 2. This is the matrix of order, square matrix of order 2. This is A is a matrix 1, 4, 3, 2. Write down the characteristic matrix of A. A is A minus lambda I, means A minus lambda I 1, 0, 0, 1. So this is 1 minus lambda 4, 3, 2 minus lambda. Okay, this is actually 1, 4, 3, 2 minus lambda 0, 0, lambda. So 1 minus lambda 4, 2 minus lambda, as I have already explained. The characteristic equation of A is determinant of A minus lambda I equal to 0. This is matrix of A minus lambda I. So its determinant will be 1 minus lambda 4, 3, 2 minus lambda equal to 0. So let me see what is 1 minus lambda into 2 minus lambda. Let me operate it. 3 4s are 12 is equal to 0. Or 2 minus 2 lambda minus lambda, it is 3 lambda plus lambda square minus 12 is equal to 0. Or lambda square minus 3 lambda minus 10 is equal to 0. Okay? Lambda square minus 3 lambda minus 12 plus 2, it is minus 10. Is it okay? 2 minus 2 lambda minus 3 lambda and plus lambda square, it is okay. Okay. This is the characteristic equation of A. As I have said that if you have a square matrix of order square matrix, then you will get a quadratic. If you have 3 by 3, then you will get a cubic. So this is it. Or you can see lambdas. What is lambda? Minus b plus minus under root of b square minus minus plus 4ac. 10 4s are 40 by 2. So 3 plus minus 49 is 7 by 2. So your lambda is 3 plus it is 5 and 3 minus is minus 2. So these are the eigenvalues. Eigenvalues of A. I hope you got it, huh? This is how to find the eigenvalues. Let me take up one more example. Question is A equal 314 026 005 0 0 and 5. You see, this is A. What is the characteristic matrix? Characteristic matrix A minus lambda I. Characteristic matrix is 3 minus lambda 1 4 0 2 minus lambda 6 0 0 5 minus lambda. Fine. Characteristic equation A, determinant of A minus lambda I equal to 0 means determinant of 3 minus lambda 1 4 0 2 minus lambda 6 0 0 5 minus lambda. Let me operate from here. It is 5 minus lambda into this 3 minus lambda 2 minus lambda minus 0 equals 0. So your lambda is 2, 3, 5. Lambdas are 3, 2, 5. You have a cubic. This is a matrix of order 3 by 3, square matrix of order 3. Characteristic equation will be a cubic and you will have 3 values of lambda. These are the eigenvalues. eigenvalues of A. Fine. Now let me come to the eigenvectors of A. Eigenvector. See, what is the definition? A non-zero column vector A, x, y, z, or whatever the values are, x, y, z, k. A non-zero column vector is said to be an eigenvector of a square matrix A if it satisfies the it satisfies the equation Ax equal to lambda x. If a column vector x is such that it satisfies the equation Ax equal to lambda x, then x is known as the eigenvector. Or Ax equal to lambda I into x, because you know I into x is x. Or A minus lambda I into x is equal to 0. So, a non-zero column vector x is said to be an eigenvector of a square matrix A if it satisfies this equation. A minus lambda I into x equal to 0. This is the characteristic matrix of A multiplied by this column vector is 0. These are the solutions of this matrix, right? Characteristic matrix. So this is it. So a non-zero column vector x is said to be an eigenvector of a square matrix A if it satisfies this equation. For example, first example, A equal, what was first example? 1, 4, 3, 2. Is it 1, 4, 3, 2? So, the characteristic matrix is A minus lambda I. 1 minus lambda, 4, 3, 2 minus lambda. This is the characteristic matrix of A. Characteristic equation is determinant of A minus lambda I equal to 0. This is characteristic matrix. This is characteristic equation. So determinant of 1 minus lambda, 4, 3, 2 minus lambda